Hello, I'm Ashutosh Bapat. SQL PGQ is the latest addition to SQL Standard. It allows relational data to be treated as if it is a graph. We have committed basic support for this standard in PostgreSQL 19. In this talk, you will get familiar with salient features of SQL PGQ standard and what has been committed recently. Let's start exploring property graphs with SQL PGQ in PostgreSQL. Let's take Ticket to Ride, the popular board game, as an example. What is SQL PGQ? It's a SQL standard, part 16, added in 2023. It introduces a concept called property graph. It is the same graph with nodes and the edges connecting those nodes, but these nodes and edges have properties associated with them. And these nodes and edges can be classified into different classes. This standard allows relational data to be treated as a property graph. It overlays a logical view on the relational data. It consists of declarative graph query language so that this graph can be queried in terms of nodes and edges and not in terms of joins and unions of rows. There are other RDBMS implementations available. And good news is we have committed basic SQL PGQ support in PostgreSQL 19, which will be released later this year. Let me introduce Ticket to Ride, a board game which I'm going to use as example. In this game, the board contains cities and routes connecting these cities. Or I will say it contains places like cities, countries, and the routes connecting these places. Each player is given few tickets and each contains a pair of these places. A player gets the points for that ticket when the paths when there is a path connecting the places on that ticket claimed by that team. It's a turn-based strategy game, and as you will see that it is a graph in computer science uh, terminology with cities or places as nodes and the routes as edges. For this talk, I'm going to use a simplified hypothetical graph as shown with the cities in blue bubbles and countries in pink rectangles connected by routes of varying length and with different points. Now let's suppose we want to use PostgreSQL to figure out how to play this game, the strategy for this game. What we need to do is first we have to convert the data on the map into relational data. So let's start creating tables. The first table is cities. It has primary key city ID, name as other column, and there is one row for every city on the map. Second, similar table countries, country ID as primary key, name as another column, and one row for every country on the map. Let's also add two more tables for the routes. One for the routes connecting cities with route ID as primary key and city ID as foreign key referencing cities. Length, color, points claimed by are columns corresponding to the properties of these routes. And there is one row for every route on the map. Similarly, for country to city routes, again the same set of columns, except that country ID and city ID are foreign keys into respective tables. And one row for every route between country and city. We started from the data on the map, which was graph, converted it to relational data. But in order to think in terms of graph and find paths which are optimal, we need our graph view back. And that's where the first feature of SQL PGQ helps. It allows to create a property graph. In this case, let's name that graph as TTR graph. There are two major components to this property graph: vertex tables and age tables. Vertex tables are the tables which contains nodes, and the age tables are tables which contain ages. You must have figured out by now that there are two tables which contain nodes, cities and countries. Their keys are the columns in the respective tables which identify the nodes. Next come label, which which give the class of that node. So all the rows in cities table belong to class city. All the rows in countries table belong to class country. And each of them has only one property name, named name, associated with them, which corresponds to the respective column in the respective tables. That's about the vertex tables. The next is age tables. Age tables have the same components as the vertex tables, but they have two more components which define the source and the destination nodes of a given age. So, and the keyword corresponding keywords are source and destination. You will see that in the first age table, city routes, we have source key references clause. It is it is nothing but the foreign key um, in the city routes table referencing the cities table. When that foreign key is clear, as is in example of country city routes, we can get rid of the key references part of that component and just say source is countries, destination is cities, so that it knows that the ages of country city routes have their starting vertex in countries table and the end vertex in cities table. Similar to vertex table, age tables also have labels and properties associated with them. In this case, we are using the same named label root for both the tables. So in SQL PGQ, a given vertex or age table may have multiple labels associated with it, or a single label may be shared across multiple vertex or age tables. In fact, we can share one label across vertex and age tables as well. The only condition is each label has to have the same set of properties associated with it. For example, in this case, root ID, length, color, points claimed by exactly the columns of the respective tables are mapped to the properties of label root. These properties need not be one-to-one mapped to the columns. They can be expressions containing the columns, or they can be expressions which may not have even the column names. All that flexibility is allowed in the standard. So we started with map, the data in the map. We converted it into relational data, added property graph on top of it, and now we can visualize that relational data as if it's a graph. The same, it goes to the map. In the next slides, what I'm going to do is I'm going to introduce features of SQL PGQ one by one. Not all of them are implemented in PostgreSQL. The ones which are implemented are highlighted in green color. Those for which there is some patch proposed, those are blue, highlighted as blue. The ones which are under design, um, they are in brown. And for the features for which we haven't even started thinking, they are in red. Okay, let's start with our first exploration. Let's start with simple one-stop route. What we want to do is we want to find all the paths between two cities, Mumbai and London, which have exactly one city in between. So we specify, in order to specify a graph, a property graph in the SQL query, we use graph table construct enclosed in parentheses. To that, we specify the property graph name. After that comes the match clause. In the match clause, we give the pattern which we want to explore for a substructure in the graph. Typically, a pattern is sequence of vertex patterns and edge patterns. A vertex pattern tells which vertices can be placed at that position in the path. Edge pattern tells which edges can be placed at those positions, at the corresponding positions in the path. For example, here we have three vertex patterns and there are two in between edge patterns. The three vertex patterns are named A, con, and B. All of them have optional three components. One, the name. Second, the label, which in this case for all of them is city, because we want to find paths which have vertexes of class city. And last is the filter condition. In this case, where a dot name equal to Mumbai for the first vertex pattern and b dot name equal to London for the last vertex pattern. So that specifies that the first vertex has to be one with name Mumbai and the last vertex in the path has to be one with name London. The stop can be any city. It cannot be country. That we specified by giving the class in the form of label. Edge pattern is similar, except that the vertex patterns are enclosed in parentheses and edge patterns are enclosed in brackets with dashes around them. These dashes sometimes have arrows indicating the direction, but in this case, they are directionless. So for both the edge patterns named R1 and R2, we are going to be using the same label. So those roots or the edges can come from either table. Given that we are constraining all the vertices as cities, only the roots between the cities will be chosen. The last part of this graph table construct is columns. So we told what substructure in the graph we want to explore. But columns tells what properties of that substructure we want to project, we want to use in the query we are looking for. So in this case, we are looking for the name of the first city, the last city, the connecting city, and the total length and total points of these paths. Before moving ahead, I will digress a bit and explain what happens to this graph query. So there are it undergoes a transformation which has three stages in it. One, we convert element patterns into element tables. Second, we convert path pattern into union of joins. And third, we replace all the property references into the corresponding column references. So when we are converting element patterns to element tables, we take the label expression, compute set of labels from it, and for every set of labels, we compute the properties associated with it, as well as the vertex and edge tables that belong to that class of labels, or the class that is determined by the set of labels. A path pattern is broken into sequence of element patterns, and for every element pattern we calculate the set of vertex and edge tables. If you visualize this as some sets, uh, like the it becomes a k-partite graph with k as number of vertex or edge tables. Executing this query or transform this query itself becomes a depth first search through this k-partite graph. So each path then gets converted into sequence of joins, that the path is a result of this depth first search. And then the set of paths, which are all the permutations of these um, k sets of elements, those are combined using unions. At the end, we convert property references into table column references. This, after this transformation, what we get is a pure SQL query. So we take graph query, convert it into pure SQL query, which is executed as any other regular SQL query through the execution engine. So on the left side, you will see the graph query that we started with. On the right side, you will see the corresponding equivalent SQL that was generated out of these transformations. And here is pictorial example of the roots that we got as a result. We are just highlighting two roots here. Next feature I want to discuss is label disjunction. In the earlier query, we were interested only in the paths that go through city, but let's say we are also interested in paths that go through countries. All we have to do is say that change the label expression to city or country, and that's it. Um, the edges are already using label root, which covers all the routes between cities as well as countries, so we don't have to change anything there. And here is the resultant SQL. All we did was a slight change in the label expression, and that resulted in double the size of the SQL query. Now there is the union leg added corresponding to the countries. And this is true with every small addition to the graph query, which results into an exponential growth of the SQL. That is the strength or power of the SQL PGQ, that it is expressive and expressed in terms of graphs rather than writing this humongous SQL. Again, example paths that we found, and you will see one more path which goes through South Africa. In real ticket to ride, we won't be constraining ourselves with just two route edges. We want we want them to be as long as possible, covering all the tickets that we want. So here we introduce concept of variable length paths. You will see that the age pattern has a little annotation to it, 1 to 5. It tells that I want all the paths between Mumbai and London of length at most 5 ages, with at most 5 ages in it. Now remember, all the features that we talked were highlighted in green color in the earlier slides. They are part of the implementation. This is brown, so it's still under design, but um, the thinking has started. These variable length paths can contain cycles, which of course we want to avoid when we are playing this game. So we specify a match mode, acyclic, to eliminate paths with cycles in them. It is red, highlighted in red, so not implemented, not even started. Next, I'm introducing a very powerful feature of SQL PGQ. It allows aggregation across variable length paths. For example, here we want all the routes that are part of the path, as well as the total lengths and total points that those paths will give us. These aggregates can be anything. In this case, it is sum, but you can use average also, or any aggregate of your choice. SQL purely does not allow aggregation across joins, but SQL PGQ, through this feature, allows aggregation of joins, taking the aggregates to the next level. See the corresponding SQL, again becoming more and more complex. I want to highlight here that this SQL was written with recursive query, but it could be also written using joins and unions, to three-way, five-way, seven-way joins. So somebody who wants to write SQL corresponding to graph query now has to leave the declarative nature of it aside and start thinking in terms of implementing it in SQL. SQL PGQ gets that declarative nature of SQL back, because now you can, with SQL PGQ, you can just declare what you want from the graph and not necessarily how you want to implement it in the SQL. That's the part of rewriter. Example routes, one route of 3 length and the other with 4 routes in it. Two paths, one with 3 routes and other with 4 routes in it. Next, I'm going to introduce feature for which I chose ticket to ride as an example. In ticket to ride, you are given multiple tickets with pair of cities. So what you want is to you explore or find out the substructure within the map which connects all these tickets. Um, and so multiple path patterns features allows that to be done in SQL PGQ. In the example query, we are specifying two path patterns. One, variable length paths between Mumbai and London, as well as variable length path between Paris and Tokyo in the same query. Don't forget acyclic, because we don't want either of those paths to contain cycles. Remember, this is blue, highlighted as blue. So there is a patch actually proposed on Hackers for this feature. I won't even bother reading the equivalent SQL. It's too clumsy to even start thinking about it. Here are example routes again. One between Paris and Tokyo, other between Mumbai and London going through Germany. As we approach the end of this presentation, I'm going to give you a quiz using a previously seen query, which I have repeated on this slide. I want you to write a query which will find whether team A has claimed all the paths connecting Mumbai and London. Supposing Mumbai London is their ticket, whether team A is going to get the corresponding points or not. You have to make a small change to this query so that it answers our question. I will come back with answer after a few slides. I want to highlight that what SQL PGQ is not. It's not a native graph database. It does not specify how the storage should be. The relational data remains relational. We do not have optimized storage specified according to SQL PGQ. All SQL PGQ gives is this declarative, powerful language through which we can explore substructures in the graph or graph patterns within the graph. Those who have been using PostgreSQL for their graph applications must be familiar with Apache Edge, which is an extension providing graph query facility on top of PostgreSQL. A natural question is, what happens to Apache Age once SQL PGQ lands in the core? I think they have a very good symbiotic future. SQL PGQ will continue to focus on SQL PGQ features, optimizing those, whereas Apache Age will continue to focus on portability, migrations. It will continue to provide the Cypher query language layer on top of PostgreSQL. It can use SQL PGQ to optimize it further. I see this relationship evolving in a similar fashion as the relationship between partitioning, which is a core feature, and PG Partman, which is an extension evolving, has evolved over the years. Of course, you may want to choose SQL PGQ when you are writing new applications. Okay, let's come back to the quiz. And the answer is all you have to do is add a where clause in the age pattern, which is r dot claimed by equal to team A. It is highlighted in green, so it is supported. It is a supported feature. With that, let me end my presentation. Thank you for watching this presentation, and we will take questions in the Discord channel. Thank you.